Our story starts off in ancient Greece with a mathematician known as Pythagoras. You must have heard about his famous theorem concerning right-angled triangles, right? Now Pythagoras, who lived from 569 to 475 BC, founded a brotherhood called the Pythagoreans. He was an outstanding thinker who made contributions to a range of areas, starting from mathematics and philosophy to music and religion. But here's the irony. Pythagoras didn't actually discover the theorem named after him. Welcome to the Maths Factor. We're going to travel back in time in this episode to explore the world of classical geometry. Pythagoras and his theorem, the mathematicians of Indian altars, Euclid's axioms, building Platonic solids, and measuring the earth. Sounds like a fun mix, eh? Well, let's set off right away. First off, let's meet up with John to explore an out-of-the-box proof of this theorem. John is attempting this with a bunch of colorful wooden blocks. First, he pulls out a sheet of paper and draws a right-angled triangle. Now on these two sides, he will create squares. One is 3 blocks long and the other 4 blocks long. To make each of these squares, he is using 9 and 16 squares. We can also represent as 3 square and 4 square. Now what does Pythagoras' theorem state? It tells us that in a right-angled triangle, the square of the hypotenuse, which is C, the side opposite the right angle, is equal to the sum of the squares of the other two sides, B and A, which means A square plus B square is equal to C square. Now John physically creates a square on the hypotenuse. How many little squares does he use for that? 25, which is 9 plus 16, the sum of the squares on the other two sides. Cool, right? Now, we catch up with Karan, who has an even more interesting demo of the theorem. He constructed a series of 3 water tanks. If we look at them closely, we'll see that we have a right-angled triangle in the center, with a square on the hypotenuse and one on the other two sides too. Now, we have filled the square on the hypotenuse with colored water. When we tilt it, presto! The other 2 tanks will be filled up with water, hence proving our theorem. We can reverse the process and reach the same result. Quite innovative, right? Back to Pythagoras. If he didn't come up with a theorem, who did? Well, one version believes that when he was traveling through Egypt, he met up with a group of people known as rope stretchers. These were the engineers who built the pyramids. They held a very special secret in the form of a rope tied with 12 evenly spaced knots. It turns out that if the rope was pegged to the ground in the dimensions of 3, 4, 5, a right triangle would emerge instantly. This gave Pythagoras the cue that led to the theorem. In this triangle, the square of the hypotenuse, which is length 5, will give us 25. Now add the squares on the other two sides, 3 square plus 4 square, which is equal to 9 plus 16, which is equal to 25, which is equal to 5 square. And there we have it. the square on the hypotenuse is equal to the sum of the squares on the other two sides. It was this knowledge that enabled the Egyptians to lay the foundations for their astounding buildings accurately. A variety of other civilizations, like the Babylonians, the Chinese, knew about this theorem many years before Pythagoras figured it out. But the earliest version of the theorem comes from India and dates back to 800 BC. It's found in Vedic texts like the Sulbha Sutras. Now, these texts give us information of the geometry related to the construction of fire altars that were used for religious purposes. So here's one extract. It says, "The rope which is stretched along the length of the diagonal of a rectangle produces an area which the vertical and horizontal sides make together." So if we take a rectangle ABCD, BD is the diagonal of the rectangle. Then the area on the diagonal is BD square, which is the same as the area of the square on the diagonal, which we called BDEF. Now, this should be the same as the area on the vertical and horizontal sides, which are AB and AD. In other words, this says area of the BDEF is equal to area of ADYX plus area of ABQP, or BD square is equal to AB square plus AD square, which is what the Pythagoras theorem states. Let's leave the Pythagoras and his theorem and take a break, but we'll be back to explore the dynamic Platonic solids, Eratosthenes' astounding theory about the Earth's surface, and the fascinating axioms that define geometry, all on the Maths Factor. Back in the Maths Factor, let's move to another great mind, the philosopher and mathematician Plato. He is possibly best known for his identification of the set of 5 regular solids, which have come to be known as Platonic solids. Now, what is a Platonic solid? Take this cube and this cuboid. Both are solid. All their faces are flat. Now, on the cube, all the faces are of the same size with edges of the same length, where every angle between the faces is the same too. This is not true of the cuboid, where the sides are of different lengths. The cube is a Platonic solid. There are many more complex ones also. An agreement is going to use these paper cuts to construct all of them. She'll start off with this paper cut, which she puts together to form a tetrahedron, which has 4 triangular faces. The acuteness of the angles led Plato to name it fire. She then builds a cube with 6 faces. The stability of the cube led Plato to associate it with the element earth. Next, Agrima puts together an octahedron. It has 8 regular faces, 6 vertices and 12 edges. The element associated with this figure is air. Then Agrima pulls out the paper cut that makes a dodecahedron. This solid has 12 pentagonal faces and is believed to be the most mysterious and powerful of the 5 regular solids. It embodies the other 4. Plato therefore said that the dodecahedron is the cosmos. And finally, Agrima pulls out a paper cut that makes the icosahedron, a solid with 20 triangular faces. Plato called the icosahedron water. And here we have them, the only 5 famous Platonic solids. And the fact that there are no more has been mathematically proven. Let's move in time and place to the famous library at Alexandria, Egypt in 240 BC. The head librarian, a mathematician called Aristophanes, was looking through an old papyrus book. He read that every year at noon, on the 21st of June, which is summer solstice, the columns of the temples in the city of Syene in Egypt ceased to cast a shadow. Now Aristophanes wondered whether a pillar at Alexandria would cast a shadow at the same time on the same day, which was the summer solstice. He checked it out and verified that in Alexandria, pillars did cast shadows on that day. Using this information, he managed to work out the measurement of the Earth's circumference. Now, we have three young people, Hari, Gautam and Kavya, who are planning to figure out what exactly Aristophanes did. There were two pillars, one in Syene and one in Alexandria. One had a shadow and the other didn't. How? Very simply, because the Earth is curved. The sun's rays come from so far away that they are parallel to the Earth. Now, if there is no shadow at Syene, that means the sun was directly overhead, right? Now, if the Earth was flat, there'd be no shadow at Alexandria also. So this implies that the Earth is curved. So the rays make an angle with the pillars at Alexandria. Let's call the angle theta. Using simple geometry, we can see that this is the same as the angle formed by the two pillars at the center of the Earth. Now, if we can figure out this angle and the distance between Syene and Alexandria, we can work out the circumference of the Earth. Our team tries to measure this angle by replicating what Aristophanes must have done. They first put a small vertical stick in the ground. They measure the height of the stick and the length of the shadow. Then they connect the two ends. Using this, Aristophanes was able to calculate the angle. Our group simplifies the process and uses a protractor. The angle made was of 7.2 degrees. The full angle at the center of the Earth is 360 degrees. So 360 by 7.2 is equal to 50. So this angle is 1/50th of the whole angle. Then this distance is 1/50th of the circumference of the Earth. What is this distance? Aristophanes actually got someone to walk the distance and counted their steps. He worked out the distance to be 800 kilometers. Now the circumference of the Earth is 50 times this, which is 40,000 kilometers. Now if we use modern-day data and measure the circumference of the Earth at the poles, we come to the figure of 40,008 kilometers. Pretty accurate, considering the time and the simplicity of his method. This demonstrates beautifully how mathematics is a tool that can help us unlock knowledge and bigger ideas. This led to the idea prevalent at the time that God must have been a geometer. Let's take a break on the thought, but we'll return with Euclid's fascinating axioms and the scientists who showed that they may not always work. Join us in just a minute on The Maths Factor. On The Maths Factor, we're exploring classical geometry. Our journey now brings us to Euclid, who lived from 325 to 265 BC. Euclid was one of the greatest of all geometers and had many publications. His most famous was The Elements, which is composed of 13 books, which went on to become one of the most influential books in the history of mathematics. Now, Euclid built these 13 momentous volumes on a series of five central axioms. Let's look at it in a bit more detail. First, what's an axiom? Well, an axiom is a self-evident, valid statement. Let's look at the 5 axioms. The first axiom said, any 2 points can be connected by a straight line. That's it. Make 2 points anywhere on a plane, no matter how far apart, and it is physically possible to draw a perfectly straight line connecting the 2 of them. Now for the second axiom. It says that any straight line segment can be extended indefinitely in a straight line. Sounds simple enough? We take the line that we drew through the point and extend it on either side. Now we have come to the end of our paper. Do we need to stop? No. Theoretically, the line can extend infinitely in both directions. In other words, there is no end to the line. The third axiom tells us that a circle can be drawn with any center and any radius. Take any given line segment. A circle can be drawn using the end point of the segment as a center and the length of the segment as the radius. Euclid has used the idea of a line to define a circle. The fourth axiom moves on to tell us that all right angles are equal to each other. A right angle is made by constructing one line perpendicular to another. Any 2 such right angles are equal to one another. Now these axioms are not particularly revelatory, are they? What Euclid did was to use them to create a whole system of geometry. Let me give you one simple example. We'll start off with a line AB, and we will come up with an equilateral triangle from this line. Now we know that we can draw a circle with A as center and AB as radius. Equally, we can draw a circle with B as center and BA as radius. Now these 2 circles will intersect at a point. Let us call it C. Now connect A and C and B and C. We know that is possible from the first axiom. Consider the triangle ABC. In the circle with the A as center, AB and AC are radii of the circle and hence equal. AB is equal to AC. In the circle with B as center, we know that the 2 radii AB and CB of the circle are equal. AB is equal to CB. From this we can conclude that AB is equal to AC is equal to BC, which means the triangle is equilateral. And so an equilateral triangle exists. Like this, Euclid used these basics to prove a proposition. This was then used to lead into a second proposition, then a third, and so on. This process is known as axiomatic approach. All pretty simple till here. Well, it all changes with Euclid's 5th axiom. This starts off with a line. It says through any point not on the line, there exists one and only one line that can be drawn parallel to the given line. And by parallel lines, we mean lines that never intersect. This seems different from other axioms, right? Not so self-evident. Many mathematicians struggle to accept this axiom. All this changed in the 19th century. The first was the brilliant German mathematician C.F. Gauss. He was convinced that the 5th postulate was independent of the other 4. He began to work out the consequences of a geometry in which more than one line can be drawn through a given point parallel to any given line. A geometry in which the sum of the angles of a triangle need not be 180 degrees. And so he developed a whole world of thinking where Euclid's 5th axiom did not hold. Gauss never published his work because he suspected the mathematical community would not be able to accept a revolutionary denial of Euclid's geometry. This is János Pálay, who worked intensively towards non-Euclidean geometry. He was a son of Farkas Pálay, who was a friend of Gauss and had discussed some of his theories. He in fact warned his son not to waste 1 hour's time on that problem. In 1823, János Bolyai wrote to his father saying, "I have discovered things so wonderful that I was astounded. Out of nothing I've created a strange new world." In 1825, he published his Strange New World as a 24-page appendix to his father's book. To confuse the issue further, in Russia, another scientist, Lobachevsky, published his theory on the non-Euclidean geometry. Neither Bolyai nor Gauss knew of Lobachevsky's work, mainly because it was only published in Russian. Ironically, in spite of so many scientists working in this area, it is only after the death of Gauss lots of unpublished papers were found revealing his work in this area, and their ideas entered the public sphere. Let's see how the geometry works with a very simple example. Take the two-dimensional surface of the globe. At the equator, the lines of longitude are parallel. Then, according as the fifth axiom, they should not meet. But they do at the poles. Again, on the surface of a sphere, the interior angles of a triangle need not add up to 180 degrees. In fact, a triangle on the surface of the Earth can be made using 3 right angles, a clear divergence from standard geometry. Today, the work of Gauss, Bolyai, Lobachevsky, Riemann, and their theory of a non-Euclidean geometry is accepted. Well, we are all done with geometry for now. We have journeyed through ancient Greece and played around with circles and philosophers, lines and globes, all in an attempt to explore the magic of geometry. Our journey today with shapes and lines ends here. For more fun mathematics, don't forget to keep watching The Maths Factor.